Really quickly, there's not much to say on my who slide. My name's Haroon. I work for a tiny company in South Africa called Thinkst. The main takeaway for you guys for that is I flew about 30 hours to get here, which is why my voice is hoarse, not because of anything that happened last night. I promise. So really quickly, one of the questions is why I bothered with this talk. And a little while back, Halva, if you're at Blackhat, you probably know Halva's name. Halva tweeted saying, can someone write a history of code exec from 95 to 2009? Okay, and this topic comes up periodically, and some guys have done some work on it. Ben Hawkes did some work on it at an Australian conference. A long time ago, Ben Nagy released a paper at EI with some of this information. But a few years ago, a big discussion broke out because someone in academia released a paper and introduced a topic called return-oriented programming, and the world basically crashed because everyone who wasn't in academia screamed that academia was stealing it. Academia screamed that these pesky hackers never give attribution for anything. What do they know anyway? And so it kind of became big news. Recently, Nico Weissman from ImmunitySec basically said the same thing again. Every time you heap spray, someone thinks he just pioneered a new technique that somebody else invented in the 90s. Okay, so basically with this talk, what I'm saying is Twitter made me do it. Okay, the Twitters convinced me that somebody should try to put all of this stuff together in one coherent talk or paper. One of the hidden reasons that I've got is to demystify part of the stuff that's kind of mystical. And while that sounds grand, my aims are simpler. Back in 2003, for example, there were lots of us saying, we can do that simple stack stuff, but once you get to heap stuff, that stuff's crazy voodoo, okay? And today, if you give someone a chance for a safe heap unlink 4, they kind of look at it and go, hey, that's easy stuff, it's the new stuff that's crazy. And so in part, when it comes to memory corruption attacks, there's a barrier to entry that stops people from fiddling. And once you're over that barrier to entry, lots of times you discover that you've got a knack for it, and people go on to do some coolness. So I'm hoping to kill some of that. And the bottom one is simple. Solar Designer clearly wasn't human. And I think it's wrong for anyone to call him human. So one of the things I did with this talk is I ended up collecting a whole bunch of data. And as a geek, the moment you collect a bunch of data, the first thing you want to do is graph it. So I graphed a whole bunch of stuff, and most of it adds absolutely no value. What you're seeing up there is simply how many talks at Blackhat covered stack exploitation or heap exploitation in the last few years. Okay, so clearly it's been a huge topic of concern. But in truth, again, the main reason for doing this talk is because Mark Dowd pointed out that chicks dig memory corruption bugs. Okay, so really quickly, I'm going to give you some caveats on the talk. I had an intention, which was to start collecting this data. The task is too big for one guy, so I need more people to jump in. And so I kind of set arbitrary limits so that I could present something, and I'm hoping that after that it kind of takes on a life on its own. So one of the first things that I did is I chose to focus only on x86, only on Microsoft, only on Windows. Now, of course, this cuts out a whole bunch of innovation. Okay, it cuts out all of the stuff that FX did on Cisco iOS exploitation. It cuts out stuff that John McDonnell did on Spark. And some of those are really bad because the exploitation that they did informs the exploitation on x86. Okay, so you'll see, we'll come to it, but lots of the ROP stuff that gets discussed today was kind of done by John McDonnell on Spark a really long time ago. Also someone whose humanity is slightly in question. But so for this talk, we kind of focus on x86. The other one of the guys who read the paper earlier pointed out that my view is myopic, okay, which means essentially I've got a very Western view of things. And this is largely because of my own inability to read Chinese websites or read websites that don't have English on it. Google Translate's not that helpful for this stuff. There's probably a wealth of information in languages that I don't understand. And periodically we see this stuff pop up. So the first SEH overwrite attack that we see coming out happened in a worm that was written by someone in China. And we didn't see that attack happening for a while. But so I'll miss that stuff. If you know that stuff, if you know people who know that stuff, go to the timeline, edit it in, it's going to be useful. This is my only lolcat in the whole talk, I promise. My point here is really simple. If you try to calculate how many hours we're trying to compress into this talk, you're looking at something like 300,000 into a 1 hour talk, which means it's going to be lossy. Every one of the techniques that we talk about deserves a Blackhat talk on its own. We're trying to do all of them in 1 hour. You're probably going to lose some information along the way. Disclosure bugs and counts. Everyone knows the R-Snake Taviso issue that happened recently. I'm not talking about that at all. What I do want to talk about, again, was another semi-pointless graph that I decided to put together. And this is one of those things when you're doing research like this that starts off like an okay idea and rapidly descends into a horrible idea as you do it more and more. So I started off saying, well, we've got OSVDB, which is a source of reported bugs. Why don't I just troll OSVDB and see how many bugs were memory corruption bugs? And so I pulled the DB and started doing some counting. And then you realize that the data needs some fixing up, so you start writing ugly bash scripts to fix it up. And eventually you've invested so much time doing it that you might as well just go all the way and do it. But what you end up with is a graph that looks something like that. And what we're looking at there in red, what you can see is memory corruption bugs as they reported, and the rest are total vulns reported. Okay, and there's a whole bunch you actually can read into this. The one thing that's interesting, Marco pointed out, is that memory corruption bugs are kind of plateauing, but they're not dipping. So while the total vulns went up and down, memory corruption bugs seem to kind of stabilize, but it doesn't mean that they're going away. The total vulns, of course, the extreme slope that you see there is because people started reporting XSS in Uncle Tom's PHP cart. So those bugs went way up. But what you notice from it is that memory corruption bugs aren't really going away. Okay, the numbers aren't dipping significantly. They still reported a lot. I've still got this data and it's still worth playing with, because it would be interesting, for example, to isolate just certain vendors from it. So if you just looked at Microsoft, Adobe, and Apple, for example, I'm sure you'd lose the noise of Uncle Tom's PHP cart, and those graphs will actually look a lot worse. So quickly, the first timeline that I decided to do, so I said, okay, we're going to build this timeline and add all of the events that were important for memory corruption on this timeline. And I kind of started with the top of mind, like, okay, I know this happened, let's Google and find out when it happened. And clearly this approach is incredibly naive. Okay, so there's just too much of data and you miss a ton. And so what we ended up doing is, if you go to that URL up there, which is a bit of a mouthful, I'll fix it and shorten it after the talk. But basically, this timeline gives you an interactive way of graphing the events as they happened. I don't have internet access here, so I can't really show it to you. But what's interesting is, for each of those items that you click on, you then get more information on that event. Okay, and you get information, you get links to more information, links to documents, and there's a few feature requests that I'll discuss in a little while. None of that stuff is actually difficult work. It was done largely because of a project that MIT have to build interactive timelines. It's literally something that took like half a day to put together. Right now, there's no authentication on it, and I don't plan to put authentication on it. So you can go there and decide that you know about this event that happened at a certain time at that event. People will look at it and alter it and argue about it. But if you feel something deserves to be there, go on, put it up. That information needs to be stored somewhere. On your CDs, you should have the paper that came out of all of this. The papers, so you probably got a better chance of gaining useful information from the paper. If for no other reason, it's way unlikely that we're going to finish all of the content during this talk. But you can pick that paper. It should be on our website when we're done. So at the end of this talk, you're not suddenly going to be able to exploit stuff left, right, and center. Okay, but what you should know is when someone says, well, that's an unlinked 4-byte write anywhere primitive, you should have an understanding of what that means. And you should be able to say, well, that used to work before, but stopped working because of the following reasons. Okay, so the first question becomes, where did all of this start? And in truth, it started a really, really long time ago. So John von Neumann was a mathematician born in 1903. Okay, and largely the machine architecture that we use today, von Neumann architecture, is the one that's on the top right there. And essentially von Neumann architecture uses the same hardware for instructions and data. Okay, so there are alternative architectures, notably the Harvard architecture that's down there, that separates instructions from data. But a lot of the memory corruption problems that we see come because we use von Neumann architecture. Okay, so the question becomes, really quickly, we needed to do a graph on memory basics, and we figured that all elite memory explanations should be done in ASCII text. Okay, I kid. So memory, if you look at it really quickly, and I'll blitz through some of this. So basically, every process on your machine thinks it gets 4 gigs of RAM. This stuff looks up on a page table to actual physical RAM. And the kernel gets mapped in at the same location. So the kernel runs it, and everything running thinks it gets its 4 gigs. This memory is further segmented. So there's segments in there, text, data, heap, mmap. Different OSs will do this slightly differently, but essentially you're looking at region of memory to store your code, region of memory for shared libraries, region of memory for the stack, region of memory for the heap. Okay, and we'll discuss why this stuff becomes important. So one of the questions is, what is code? Okay, on your machine, what you're looking at there is just a random hex dump of some running process. And if we look at that stuff, okay, the question is, what is that stuff? Okay, and in this instance, the instruction pointer looks at it and says, that stuff's code. Okay, and so it executes, if the instruction pointer got there, it would execute these commands. Okay, and the problem is, if you looked at this, which looks like instructions also, and you looked at it in the dump, you can't tell that actually that's just data. Okay, so that's just a string. And again, this comes back to the problem of using von Neumann machines. Okay, data can be instructions, and instructions can be data. Okay, and this is a problem that we're carrying around for a bit. So really quickly, I'm going to add another caveat. Last year, we did a talk on hacking cloud stuff, and we ended up trying to do like 100 slides in the hour that we had. So this year, I've only got 38 slides, so we should hopefully make it. But instead, I've decided to try something new, which is Prezi, which has something like 160 slides, which might explain why I'm talking really quickly. So the point of this talk, again, is to examine that timeline of events as they happened, and we'll try to take them almost completely from the beginning. Okay, so one of the things that should surprise you is the first documentation of memory corruption attacks actually happened in 1972. Okay, there was work done for the US Air Force that basically documented stack smashing. It went into detail in several locations saying this is what happens, parameters are not checked, you get to overwrite a return address, bad stuff will happen. Okay, the really important thing to note there is that date. It's literally before I was born. Marker is a different story. So I'm going to blitz through. FRAC 1 was published. When FRAC was originally published, it was a freaking magazine. But because so many interesting things get documented in FRAC over the next quarter century, the starting of FRAC at least deserves a mention. So Taran King, Night Lightning set it up, and it actually becomes valuable. In 1988, the Morris worm ran around the internet. Okay, the Morris worm is interesting. So it's the first worm that ran around using a buffer overflow as one of its attack vectors. There's a few things that are interesting here. Lots of the stuff's been said. Robert Morris was a student at Cornell. He's now a professor, I think, at MIT. And he exploits a buffer overflow in the finger D daemon, okay, which is a vanilla stack smash. And what's really interesting to me is when you look at it, Robert Morris's father was the chief scientist for the NSA. And up until this point, you kind of give Robert Morris credit for having figured the stuff out himself. He's certainly smart enough. But when you consider that the military were already documenting buffer overflows in '72, and the son of the chief scientist of the NSA releases a worm that exploits a buffer overflow, you start to think that maybe there's a little bit more to that. So with Morris's overflow, I'm going to skip through this stuff. I'm guessing all of you know it. Basically, until Morris released his worm, people looked at buffer overflows and they were looking at overwriting other variables on the stack that were interesting. So there's a is authenticated or is super user. You overflow your buffer into that buffer and you make it something else. And what Morris's worm instead did was exploited the return address pointer. So when a function is called on the stack, basically the EIP is saved, an instruction pointer location is saved, which says when you finished with this function, come back to this point. And essentially what Morris did was overflowed his buffer, went into that return address so that when the function left, it goes to code of his choosing. We'll see that stuff pop up a few times, so I don't need to go into it too much here. So in response to the Morris worm, CERT was formed. Okay, so DARPA gave some money to SEI at Carnegie Mellon and said, form CERT so that when bad stuff happens in the future, you guys can spring into action. Okay, what's interesting is already with the Morris worm, the reports were very widely on how much it actually cost. There's estimates of like $100 million. There just weren't that many hosts on the internet. So Zada's Security Digest was formed, which was later becomes the core mail list. But basically, it's a place for people to openly exchange information on buffer overflows. What starts to become interesting then is people start reporting to CERT these buffer overflow bugs in various operating systems. And it's really cool to see some of that old stuff. If you go to the timeline, click on it, you should get a link to it. Because you see the difference in the way guys were reporting it then. So most guys go, we found this bug, here's a patch for Apache, or Apache should do this differently. There's a not so subtle difference there. The next thing that's interesting here is in 1990, Barton Miller, who was a professor, published this paper essentially on fuzzing, okay? And in all the hacker versus academia arguments, you'll see with this timeline, there's quite a few times that academia actually put the hacksaws to the post. Okay, so this was way back in 1990, and they basically wrote some really simple fuzzers and essentially documented it saying, we can crash 30% of any Unix utilities just by using this simple fuzzing. So in '93, Scott Chasen forms BugTrack, and already you see the split. Basically, they were annoyed that CERT weren't practicing full disclosure, so BugTrack was formed. And in '93, it's kind of arbitrary to throw it up here, but the ISS scanner was released. So you start to see commercial stuff moving into it. In '95, Thomas Lopatic, I'm probably going to mispronounce quite a few names, this won't be the last, basically publishes this bug in NCSA HTTPD. What's really interesting is Thomas Lopatic goes on to do really cool stuff. He speaks at Blackhat a few years later, and he becomes quite an early influence on lots of the guys doing memory corruption stuff. So I'm going to blitz through this. Satan was released in '95. So Dan Farmer, Vitsa Venema write the security auditors tool for analyzing networks. It was written in Perl, basically tries to break into a whole bunch of stuff. And lots of guys objected. Some objected just because it was called Satan. And so actually what few people know is that they had a little script called repent And if you ran repent, it would rename all references to Satan Santa. That's completely pointless information. So in 95, there's a bug released in syslog-D, and I'll tell you why that's important shortly. But then a little later in 95, Mudge, or Dr. Mudge, Peter Zutko from The Loft, releases a document or writes a document called How to Write Buffer Overflows. Sadly, this document wasn't released to everyone when he released it. So the dates on the document show that it was 20th, 1995. Most people saw this document much, much later. But essentially, Mudge wrote this document to himself to remind himself how to do buffer overflow exploits. So it covers some of the basics of the exploits, some stuff that's wrong, some tips for shellcode. All in all, it's a pretty decent stab at it. In 95 also, the split VT exploit was published. Now, I'm not going to go into lots of exploits except where they fundamentally changed stuff. One of the reasons why I've got the split VT exploit is because Dave G and Vic M published it, and Dave G is the Dave G currently from Matisano. So he becomes one of the people who's still doing the stuff that was publishing way, way back. And they published this exploit code, published the bug again on BugTrack, and I'll come back to that. And then the big defining moment was in 96 when Aleph 1 published Smashing the Stack in Frac. And I'm sure all of you have read Smashing the Stack at some point. If nothing else, it's probably the most widely quoted paper there is. And what Aleph 1's attack did, much like the Morris worm, you had a buffer on the stack, you overflow the buffer, at some point you overwrite the saved EIP, which says, where should I go to next? And the technique that he documented was, put code in your buffer, and when it asks you where to go to next, point back into your buffer. So effectively, you give it some code, you give it where it should go to next. When the function returns, it returns to your code. Okay, what's interesting is the split VT attack that I spoke about used a slightly different technique, and what they did was they stored their shell code in an environment variable. They still overwrote EIP, and basically they said, go to the environment variable to execute our code. But what you should see here is they become very simple patterns. Okay, so it's, if I overwrite EIP, I get to say, where do I want code to go to next? The next part of the problem becomes, where should I put my code so that I can find it? And Aleph 1 said, put it in your injection buffer, and Dave G said, put it in an environment variable. But you can see at that point, the state of the art was, overwrite EIP by telling it where to go, and then control where it goes to. Okay, so we'll do some moving stuff. BugTrack basically hosted a conversation on stack smashing defenses, and most of the conversation was pretty architecture specific. But then in 97, something interesting happened that doesn't really get justice with that one bullet point. And basically, Solar Designer publishes the superprobe exploit. And what's interesting here is he overwrites function pointers to get code execution. So there's a function pointer, basically says, go to this location to do stuff. By overwriting that, instead of overwriting EIP, when it goes there, it goes to his location to execute code. Okay, it's an attack vector that becomes more interesting many, many years later. The next thing that's interesting there, basically core, I've seen a bunch of guys with core t-shirts today. So that same core, the Argentinian core, and SNI publish a document on DNS poisoning and an overflow in bind. Part of the reason I've got it up here is, by my reckoning, that makes core one of the companies that are actually still publishing interesting overflow stuff over the length of this timeline. They certainly deserve shouts. So then, if we go back to Skynet, in 97, at some point, Solar Designer says, well, hold on, all of this has a common feature. We're putting code on the stack, and then we're jumping to it. How about if we just say the stack is not executable? Okay, so he does this, and he quickly writes a patch, because that's what you do if you're Solar Designer. You quickly write a patch for the Linux kernel, and you make the stack non-executable. And then a little while later, he actually publishes an exploit for his non-executable stack. Okay, and essentially what he does is, he says, well, we made that stuff not executable, but there's a lot of other space that's still executable. So it doesn't matter if we've made the stack not executable, we can do clever stuff with other areas of memory. And so what he documents then, he uses the LPR exploit against his patched server, is he basically says, he overwrites EIP, but now when he tells it where to go, he doesn't say go to this location on the stack. He says go to this location in shared memory where systems lives. Okay, so the system command that's living in libc is marked executable. He says when you're done here, go to system, and here's the parameter for system. Okay, and you can't make system not executable, so effectively he returned into libc and got code execution that way. Okay, he then issued a patch to defend against that attack, which was basically to alter the way mmap was done, but you'll see even he comes up with ways around this later on. So nmap was released after that in frac, and then in '97 we see a big development in anti-exploitation technology. Basically, Crispin Cowan, also in academia, just putting it out there, invents a patch for GCC. And essentially what he does is he looks at the problem and says, well, when you overwrite this buffer, you keep overwriting stuff and then you overwrite EIP. How about if we put a canary between that buffer and EIP? And if the canary was ever trampled on, we'd know it was trampled on. Okay, so he invented a patch for GCC, and he did it for an ACM conference, but he pre-announced it on BugTrack on the 18th, and on the 19th, Tim Newsham sent a mail saying, these are all the reasons why actually that's not going to stop anything. Okay, and Tim Newsham's another one of those guys who've actually made serious contributions to the state of the art, and you don't see that much from him. And essentially, or you don't see that much of him now, is essentially the attacks that he spoke about were overwriting other local variables, and he also documented ways to leak the canary value. So if there's this canary on the stack and I'm going to overwrite it, if I could overwrite it with what it was, then when you check, you wouldn't know that it was overwritten. Okay, and StackGuard makes some jumps after that. So they started off doing a zero-based canary, and then they made it a null-based canary, and then a random canary. And you start to see that battle that'll play out right till today in terms of mitigations and attacks against these mitigations. In '98, Kristen Rue, Dilldog, also of the Loft, publishes his exploit against Windows 95. It was nostalgic just finding that image on Google Images. But what's interesting is that it was a heap overflow. Okay, but it's a very app-specific heap overflow, and at this point he documents it richly, puts out an exploit for it. More importantly, later that year he publishes the Tau of the Windows buffer overflow. And that becomes the template for guys writing overflows against Windows machines. It basically becomes the most quoted Windows exploit paper. In '99, Shock, so Matt Conover, who was, I think still does, heads up WooWoo, basically published a paper on heap overflows. And it's a really nice paper. It's interesting to read it, because when you go back and read some of these papers, again, on the timeline, hope you saved that URL. Basically, what you find from Matt Conover is he goes to great length to document previous work done in the field. So he basically quotes all of the stuff that Solar Designer did and all of the stuff this guy did, and says all of that leads him to where he is. And the crux of his paper was, hey, the heap's also fair game. If you can overflow stuff on the heap, we can probably make bad stuff happen. Okay, MITRE forms CVE, I'm going to skip through that. In '99, again, way ahead of his time, Dark Spirit, who you should recognize from the picture, is Barnaby Jack, the guy who jackpotted the ATM on stage yesterday, publishes in frac Windows 32 buffer overflows, location exploitation prevention. What's interesting, and it's kind of subtle, is already in this paper, you start to see the kickback against BugTrack. So he publishes it in frac and goes, bug track moderator, don't hate me, I used a known bug to publish this. So you start to see that bug track that was formed because the other guys weren't disclosing fully starts to get accused of not disclosing fully. His stuff was interesting. He showed how to trace to find bugs, but probably the most interesting contribution of his work was he introduced register springs. Okay, so on Windows, you most often find multi-threaded applications, and when you say jump, you actually have a good chance of not knowing where you are. And what he introduced in his paper was, when you overwrite EIP, don't just tell it to jump to the stack because you don't know where the stack is. Find another DLL that's at a consistent place that has an instruction that says jump to the top of the stack, point to it, and it will make you jump to the top of the stack. Okay, it's a level of indirection that basically gives your exploits reliability, and you should notice it's also one of the things that start down the ROP debate. The frame pointer override was pretty cool. Klog published it in Frac. Again, I won't give it a lot of attention, but essentially what Klog found was under certain circumstances, if you could just overwrite 1 byte of the saved frame pointer, when execution continued, you could make bad stuff happen. Okay, and the reason I'm skipping it here is you'll come up against it now in 2010 when we discuss attacks against ASLR. So format string bugs then made a showing in 99. And it was interesting the way it happened. Basically, Tim Toolman makes a post to BugTrack saying, I was auditing FTPD. When you do this, you can get a shell. And until that point, not a lot of people even knew of the attack vector at all. I'll come back to format string bugs in a little bit. I'm not going to pronounce that name at all. He published advanced buffer overflow exploits, but this period was basically dedicated to guys doing cool stuff with shellcode. So don't just pop a shell, bypass get UID and set UID, bypass filtering, put in alphanumeric shellcode, stuff like that. In 2000, you'll see a few documents on bypassing StackGuard and StackShield. Later, a more interesting document shows up on Frac for smashing C++ V pointers. And the reason why it's interesting is it's one of those attacks that still live. But essentially, when C++ objects are created, they create a table of function pointers. And essentially, if you remember, we were saying, well, what do we look for to overwrite? If you've got a table of function pointers sitting somewhere, it becomes interesting and worth targeting. Again, something that we'll come to in a little bit. In 2000, basically Twitch at vicar.org, cool name, published a paper on non-terminated strings, the danger of non-terminated strings. And everyone knew that stir copy at this point was bad. Okay, it's an unbounded copy, bad stuff will happen. And one of the points of Twitch's paper was even the blanket recommendation, use stern copy instead of stir copy, was also dangerous. Okay, and if you read the man page, stern copy basically will tell you that if the buffer matches the size, it's not null terminated. Okay, so if you tried to put something that matched the size of the destination buffer, stern copy won't null terminate. So essentially, if you were looking at 2 buffers that happen to live in memory like this, and you copied from buff 2 into buff 1, because it was bigger, it wouldn't overflow, but it also wouldn't null terminate. Okay, so you'd end up with something like that. And what you should see is if you try to print buff 1 at this point, buff 1 is going to tell you it's all of that because it's not null terminated. Okay, so it starts to become attackable possibly later on. So WUFTPD, an exploit was published basically with that tagline, WUFTPD providing remote root since at least 1994. And I remember speaking to FX a little while back who basically said that he thinks WFTPD is the equivalent of OWASP's WebGoat, where they took one piece of code and tried to put as many bug classes as possible in that one piece of code. But it was instructive. So what's interesting here is when Toolman published his, hey, these are format string bugs, people didn't really take notice. You weren't running ProFTPD, you probably canned it. This was an exploit for WUFTPD that suddenly showed up in the wild, giving you remote root using a format string bug. Okay, and so suddenly people went, hey, what's this format string stuff? Okay, following that, him published a 200-line paper on format strings on BugTrack. And considering it was a 200-line paper, he was actually really comprehensive. He gave examples of how the exploit works, why it works, pointed to other FTPDs that had the same vulnerability in it. But interestingly enough, he did the first serious documentation of format string bugs, and very few people actually credit him with it. So one of the things when you discuss format string bugs is that people will quickly tell you that it's really easy to spot a format string bug, so it very quickly got hunted into extinction. And this is true. Static analysis finds format string bugs. So as a bug class, it was one of the first bug classes to almost completely disappear. Okay, which of course makes that OSVDB trolling that I was doing interesting, because what you find is that as late as 2009, Oracle was still patching format string bugs in their Oracle server. The other thing that I'll quickly pick on here is, if you notice, it took them 2 years to fix that format string bug. And just to show you that it wasn't once off, they actually had 2 format string bugs, but this time it only took them a year because clearly they put processes in place. So the next thing we touch on, again, is to go back to Skynet. And basically, Solar Designer made this really low-key post to BugTrack titled JPEG COM Marker Processing Vulnerability in Netscape Browsers. And like most of his posts, there's lots of information in it. On the one hand, he basically points you to file format bugs that will become rich hunting grounds for the next few years. And then he says, hey, read this whole post because you'll probably get more information from it. And essentially what he did was he documented the first use of heap exploits as really reliable generic exploits. Okay, and essentially what he did was he showed how to attack an unlink operation. Okay, so really quickly, a doubly linked list is a computer science data structure, and essentially you've got these elements that have a link to the previous element and to the next element. Okay, and so because of what it's named, most guys will call this the F-link and the B-link, the forward pointer and the previous pointer. Okay, so what we're focusing on here is node 8 that sits in the middle of 7 and 9, funnily enough. It has a back pointer to 7 and a forward pointer to 9. Okay, and what Solar essentially documented was that when unlink is called, so if you wanted to remove 8 from this list, essentially what you would have to do is go to the previous node. Okay, so you're going to go to 7 and point it to 9, and you're going to go to 9 and point it to 7. Okay, it's perfectly simple. You're basically removing that node from the list and saying, here's who you should be pointing to as your next guy, and here's who you should be pointing to as your previous guy. But what you should also see is this becomes a form of a write what, where. Okay, because if you can say, in place of my previous pointer, if you can say write this at EIP and write this value, essentially what it's going to do is go to that location and write that value. Okay, and suddenly heap overflows that were until this point considered almost not exploitable suddenly become trivially exploitable, and it's still a bug class that lives today. Horizon, John McDonald, is supposed to have said something like, we're all just finding out stuff that Solar Designer forgot to write down. So format string attacks, there was another paper by Tim Newsham, again, covers the whole thing. It's worth finding and reading just because he's got a really interesting writing style. So he starts off his whole paper talking essentially about you at a dinner party and a friend comes up to you and says, what's a format string bug? You're nervous, how do you react? It's fairly interesting in a geeky sort of way. So in 2000, PAX releases, and essentially PAX is a patch for the Linux kernel that tries to end exploitation. Okay, and we're going to see PAX coming up again and again. Essentially what PAX does is the x86 processor at this point, the page table doesn't support a bit for whether something's executable or not. So it basically says, is the stuff readable or is the stuff writable, but everything's executable. And so PAX uses some clever mojo that we'll discuss later to basically force protection on regions of space. The mprotect patch that they added was then to try to defend against Solar Designer's return to libc attack. The detours section, at this point in exploitation, we're looking at, we've got these attacks, we still get to choose where we want to write, and people were basically coming up with, well, let's find cleverer places to write. Okay, and Juan M. Belo Rivas published a paper that essentially said, applications compiled in GCC have constructors and destructors, so code that runs before or after something, and these destructors exist whether you compile them into your code or not. So essentially he said if you can overwrite a destructor instead of overwriting EIP, when the application ended, the destructor is run and your code executes. In 2000, Brad Spender released GR Security. Spender becomes interesting if for no other reason, because if you don't know him, you should go back and Google Brad Spengler or Spender and his post to the Linux kernel mailing lists. Essentially, he does GR Security, which works very closely with PAX, and it's a whole bunch of security mechanisms for Linux that PAX doesn't cover. So in the future, it'll become RBAC and it'll become ACLs and stuff like that. In 2001, IIS, the IDA ISAPI bug hits wild, code red goes out. There's fancy graphs showing how many things were exploited that we'll skip because I'm running out of time. In 2001, PAX introduces address space layout randomization. Okay, there's two things I want you to notice here. One is, it's safe at this point to think of PAX as a spoiler of this presentation. Because without PAX, you can kind of look at the timeline and everything kind of makes sense. There was an attack, there was a defense. With PAX, everything breaks because PAX solved lots of these problems way back in 2001. People just weren't using it. So with address-based layout randomization, you'll remember in terms of the attacking that we're doing, we get to say, we're going to overwrite stuff, what should we overwrite? One of the fundamental things that we need to know is the layout of memory. Where is system living? Where is my EIP living? Okay, and PAX's solution at that point was to randomize memory. So even if you overwrote a buffer, even if you got to say where you should go next, you wouldn't know, okay? And you'll see this solution show up in commercial systems in a few years. So Stack Ghost was released, which is a kernel patch, Format Guard to protect against format bugs. Format Guard was also by Crispin Cowan, but like I say, the bug class died everywhere except Oracle, so didn't really take off. There were two papers in FRAC that essentially documented Solar's attack. The first one, Voodoo Mallet Tricks, basically went into great detail on the Doug Lee allocator, gave a lot of information on how you can exploit these things. What's interesting in 2001 is Nergal, and I'm probably mispronouncing that, published advanced return into libc exploits. And if you look at the documentation on what return-oriented programming is today, you almost couldn't tell the difference with what Nergal's published way back in 2001. For those of you who don't know him, so he published exploits then for almost everything, and today he works for Joanna Rutkowska with Invisible Things Labs, which gives you a scary amount of talent in one place. In 2002, Dave Vitale publishes Spike, his block-based fuzzer, kind of revives interest in fuzzing and basically points out how many applications fall to fairly simple fuzzers. Halvar Flake then does a talk called Third Generation Exploits. And Halvar's talk was interesting for a whole bunch of reasons. The one thing is he showed Solar's 4-byte unlink exploit on the Windows platform, okay, which wasn't done up until that point. He then documents heap attack against Borland's heap allocator. He also goes on to explain SEH attacks, okay, which I'll diagram a little later, but which doesn't get found out for a few years. Interestingly, when he documents the SEH attacks, he credits TISO, which was the hacking group at the time that basically ran the scene. I was speaking to one of the old TISO guys yesterday, and he was saying that people used to complain that TISO dominated the scene, and in truth, TISO was the scene. There was just nobody else who cared about reliable exploits like that. Okay. Interestingly, also, when you consider how old it is, there was already the talk of the no more free bugs. Okay, so that's straight from Halvar's talk, and he basically was talking about the save the bugs movement. And it's really easy to think that Halvar knows all. He possibly comes close, but also from his paper was this line that basically said, goodbye fuzzing, 2 gazillion Perl scripts. He basically said bugs are getting too hard to find, fuzzing's not going to find them anymore. If any of you went to Ben Nagi's talk yesterday, you'll know that this isn't true. So in 2002, Visual Studio adds /GS compiler protection. There's a few things that are interesting about this. The one is, it might look slightly familiar to you if you remember what we said about the stuff that Immunix did, Crisp and Cowan did. Okay, they basically put a cookie on the stack and spot if that cookie is overwritten to tell you whether bad stuff has happened. And what's interesting is for a long time, Microsoft basically said, no, we didn't look at StackGuard, we did it on our own. And the next day, they were proven right because Cigital found bugs in GS that actually StackGuard had since fixed. And basically said, well, if they did look at StackGuard, they would have known about those bugs and fixed them also. So I've just been told I'm horribly out of time, so I'm going to swing through stuff. You can see we're only on 2002. Dave Litchfield basically does red to libc on Windows. Tyler Durden attacks PAX, again, in FRAC, but he introduces an interesting concept. He basically returns to a function that outputs something to the attacker. Okay, and it's the first use of it that I could find, but essentially if you have this function that says your username is incorrect, he returns to that function and passes it a format string argument. So essentially, he's turning his buffer overflow into a format string bug and leaking information back to him on the state of your stack. Okay, and it becomes interesting. It becomes one of the attacks that we still use today. So Gera, or Hera, if you pronounce it right, does stuff at core. Integer overflows get made known to the public. So Blackhat, Neil Mehta, Mark Dowd, Chris Spencer, Halvar Flake, Nishad Herat, which gives you just about the scariest combination of brains to human ratio on a Blackhat stage. All give a talk on auditing Windows. They basically give a bunch of bugs, but the main thing here was they spoke about integer bugs, which up until this point was largely unknown. I'm going to start skipping through stuff capriciously. Nice word. Syscall proxying, the core guys basically introduced some shell code that says your shell code shouldn't just pop a shell. Your shell code could do more useful stuff. Okay, and so Maximiliano Casaras, I don't know why I bothered, basically gives credit to Tim Newsham, Oliver Friedrichs, Hera again, and Luciano Notta Francesco. And basically they start advancing the state of shell code. Essentially they say, when we inject shell code into your process, why don't we inject a full-blown server that mirrors your stack so that we can do cooler stuff with it. GR security gets a learning mode, starts getting ACLs. StackGuard and StackShield keep getting a beating. So I've got a really quick pointless demo here just because people like pointless demos. But what's interesting is the slapper worm comes out that starts targeting Apache mod SSL. And the reason I chose this bug to show was for one reason, because at the time, the original bug was documented by a guy called Solar Eclipse, which not too many people would have heard of. And in fact, he sounds like someone trying to rip off Solar Designer. But it turns out that actually Solar Eclipse will go on to do much coolness. And what you notice about his bug, or you won't really notice, is it's a worm that attacks a heap overflow, But essentially what he does is uses an information leak to fully understand the remote memory space before launching his attack. Okay, so I think there's a really nice picture of it done by Peter Zor. But essentially, during the SSL key exchange, what he does is overwrites part of the certificate with the remote memory structure. And then by looking at the certificate, gets to say, well, that's what your memory looks like, so I can target my exploit really nicely. A solar eclipse, by the way, is Alexander Sotorov. So he goes on to do much more coolness as time goes on. So PAX releases a different way to do segmexec. Absolutely at about halfway of my slides, and there's a lot more to do. So I'm going to start skipping to pointer stuff. Metasploit released. The joy of Metasploit actually becomes that Metasploit gets used more for vuln dev than just for exploits, which is interesting. PAX starts to do more cool stuff like non-exec pages. Dave Litchfield then gets credited with documenting structured exception handling attacks. Okay, and this is the attack that I said that Halvar did in 2002. But essentially what Dave documents is that structured exception handlers save a structure on the stack that basically points to the next structured exception handler or has a function pointer to code that should execute when bad stuff happens. And essentially by overwriting the structured exception handler and then causing a fault, when bad stuff happens, your code executes. So I'm wondering how much of this I should skip. Okay, so I'll go through really quickly and have them force me off stage. So safe SEH, Microsoft sees this problem with SEH. They introduce a linker flag that says, at link time, we'll make a table of all structured exception handlers. And if you're not in that table, then you're not one of our exception handlers. Sadly, Dave Litchfield then publishes a paper on attacking Windows Server 2003. And he basically figures out that if you have a DLL that doesn't have an entry at all in that safe SEH table and points to a location that's outside of the DLLs the app knows about, it will allow you to point your SEH handler there. I don't know why Microsoft would make such a silly mistake, but it was there and then they fixed it. Interestingly, GS was then fixed, and essentially what they did also was reordered the variables on the stack. Okay, essentially what they said was, if buff is going to overwrite stuff, along the way it gets to overwrite a pointer and a variable. Let's move buff so that if it overwrites, it doesn't get to attack integers and pointers on the stack. Interestingly, this is a technique used by ProPolice called the ideal stack layout, but was also invented independently, I think. So Mostef was out, the Witty worm happens, which is a worm that targets ISS specifically. Matt Conover, Oded Horowitz give a talk on how hard it is to exploit XP-SP2, and then the big thing that happens is XP-SP2 ships. Okay, and XP-SP2 basically becomes the first time that Microsoft unleash all of their mitigations in their OS. All of XP-SP2 is now compiled with /gs/safe-sh. They start doing safe unlinking. So if you remember Solar's unlink check, when they unlink, they now do a check that says, are you pointing to what I think you're pointing to? Okay, so they kind of attack that class of bugs completely. I'm going to skip through a lot of these. Hovav Shakum basically publishes a paper on ASLR. He basically says that 32-bit address space is too small. So even if you randomize stuff, you can't get enough randomization. You'll still find stuff still predictable. And he launched an attack against Apache with PAX that basically brute forces by returning to sleep. And he keeps running this attack with what he hopes is the address of sleep. And at some point, Apache sleeps. And he's now figured out the location of sleep in the memory space. And using that, he can start figuring out other parts of memory. So heap spraying starts getting popular. Skyline essentially puts out Internet Exploiter, which means your browser runs, it sprays the heap with shellcode, you then jump to it. Essentially what they're doing at that point is saying, I don't know where my stuff is, but if I can do enough of it, I can hopefully find it. There were a whole bunch of attacks that happened against XP-SP2, Alexander Ansimov. Barnaby Jack publishes a paper on remote kernel exploitation, step into ring 0. And then the big thing in 2005 was a bug was found in PAX by the PAX author. And essentially he looked at the bug and said, people used to trust PAX, there's a bug in it, I'm going home, and said he's not going to do this anymore. Nobody else took up the project, although Spender said he would, so he's still there. Process Talker was released. I'm going to skip through this. Matt Miller releases WenTrust, which is third-party ASLR for Windows. In 2005, So Be It at XCon publishes Windows kernel pool overflow exploitation, essentially doing Solar's heap attack in the Windows kernel pool. And his paper then documents what you can target if you're in the Windows kernel. So Nicholas Fellier publishes stuff. There's some bugs in format strings that come up. The other interesting thing that happens in 2005 is Sebastian Kramer publishes the borrowed code chunks technique. Now he published it specifically targeting x64. So by right it shouldn't be in here, but because ROP leans on it so heavily, I've included it. We'll come to it in a few seconds. Matt Miller again, and clearly Matt Miller inherits the super frightening bug guy title. Basically documents how you can bypass hardware dep by doing a return into libc attack. And what he does here is returns into a function that Windows has to unprotect memory. Okay, so it's pretty much what you've seen different. Visual Studio ships, essentially they now put on the strict pragma. And one of the things that they do is they now make shadow copy of arguments. Okay, if you look at the diagram up there, when we do our overflow, one of the things that we can overflow are the arguments to the function. Okay, and so if we had a piece of code that essentially had two buffers, did something with the first buffer, did something with the second buffer, and then returned, by overwriting the argument, we could overwrite important parts of the function before return happened and essentially before the cookie gets checked. Okay, so I suspect I'm going to get kicked off stage. I'm going to start. I'm going to look for stuff that's interesting. So again, Scape comes up with a technique to prevent exploitation of SEH overrides. Essentially what Scape does is he adds a guard frame. So it's called SE hop, override protection. He adds a guard frame to your SE handler chain. And so when you see those chains of structured exception handlers, before calling them, you walk the chain to see if the last one has your guard structure, and if it doesn't, it means someone overwrote it. What's interesting about this technique, there's multiple things interesting on it. One is it didn't require a recompile anymore. Okay, where Safe SEH required a recompile, his doesn't, and he built it individually, and I believe it's now included in Windows and is licensed from him. So I'm going to skip through this and see if there's anything else that I really want to say before I get completely kicked off stage, because I am. A talk gets done by some English guy. So Ollie Whitehouse does a talk on analyzing GS and ASLR, basically looking at the randomization on it. Comes up with a few points where stuff's not looking so cool. All of this stuff should be in the paper, so you should be able to go read the paper, read the timeline, and see it. I'm going to skip through all of this and quickly get to the conclusion, just so that we can maybe take a few questions. Just because I've completely run out of time. The crux of the matter is, if you look at where we are today, it used to be that everything was exploitable. We then put in dep, which says stuff's not exploitable. Dep can be bypassed with ret to libc or ROP attacks. We then said we need ASLR to beat the ret to libc and ROP attacks, except a single leakage essentially defeats ASLR. So you just need one example of being able to eke out information on the target memory space, and you can start working to bypass ASLR. If you guys went to the ponies, Dionysus Blazakis won the pony for most innovative research, and basically what he found was, also in the paper, also in the timeline, that if you put down Flash, the way Flash implements their dictionaries allows you to infer stuff about the target memory space. So stuff gets implemented in dictionaries and you can find out where they tagged. The danger also comes up of partial overwrites, which is something that we discussed with Klog's attack a way long time ago. Essentially, only the top 2 bytes are randomized. If you do an overwrite of the least significant bit, you can hop up into parts of the process space that's still interesting. Essentially, devices are becoming more active, which means we have to use ROP. Okay, if you look at iPhone, iPad style devices, attacking them is harder. It does require you to jump through more hoops. It will raise the bar significantly for attackers. And then on a completely down sour note, recently Secunia published a document that basically examined a whole bunch of Windows binaries to see if they were using DEP and to see if they were opting in so that they could get the benefit of ASLR. And I think at the current point, the only 2 they came up with, well, the one that they came up with was Google Chrome using DEP and ASLR. They had Flash Player using ASLR. And essentially, DEP without ASLR is less useful. ASLR without DEP is less useful. So unless you've got them both, it's not going to help. So what we're seeing here is that Microsoft's made these changes. People now have capabilities to write safer code. People just aren't. The bottom line, what ASLR and DEP take away from the attackers, attackers get back in terms of rich client-side applications. If you look at the work that Alexander Sotorov did with his heap feng shui paper, essentially he gave you JavaScript libraries that give you fine-grained control of the target heap. If you look at the stuff that people are doing with JIT spraying, essentially it's fine-grained control of the target heap, and all of it's interesting. For the future, information leakage attacks are interesting. If there's stuff that we missed, not because I skipped those slides at the end, so stuff that I missed earlier, please go to the site, add them to the timeline. There's a whole bunch of people who added to the timeline already, and for them I say thanks to Marco, my beautiful assistant. We clearly don't have time for questions, but feel free to mail me, visit the site, or ask me questions on Twitter. Thank you very much.